a good break. Thanks so much for all the great questions you've had already. It's been really fun discussing with you all, and it's also really fun to hear about all the different kinds of backgrounds you're coming from to this angle. So I've had a chance to speak to physicists, the category theorists, and I wish I understood better this kind of perspective. I'm actually trying to learn category theory now myself, so I can relate to that. But it's been great, the feedback that I got so far. Please keep it coming. I just heard, actually, unfortunately, that the next speaker has COVID, so won't be able to deliver his tutorial. So I will actually probably be with you for 1 extra hour. I hope you'll be able to bear with me. Okay. Okay, I'm going to do my best to try to make it as fun as possible. So we left off the previous tutorial having just derived the necessary conditions for a permutation equivariant model on graphs. And I've told you that kind of to build this model, what we would probably really like is a local function that looks at a node and its immediate neighborhood. So just to recap, to show you the picture once again, we want some function phi that will meaningfully look at a node, its immediate neighbors, and update the feature representation, right? If we can do that and stack the output vectors together, we can then build a model to solve all 3 of these principal graph tasks, okay? But as I said, I haven't yet told you how to actually implement that local function. And that's actually the essence of most GNN research that's happening nowadays. So all fundamental GNN models are just talking about a different way to implement this local function to a large extent. So let's talk about them. This gives us our 3rd part of the tutorial, graph neural networks, specifically talking about how to do permutation equivariant learning on graphs. So I mentioned it's a super intense area of research. I can have no hope of even understanding all of it myself because there's 12 new papers coming out every single day, and it's just not possible. And I would imagine, unless there are any superhumans in the audience, that probably you would struggle in a similar manner to myself. However, can I help you in some way make the whole process a bit more sane so that actually when you read about a new model, you don't have to read through the whole paper to understand what's going on, but maybe quickly categorize it into some types. So categorizations, I found they're very useful when you have to navigate a rapidly emerging field. And fortunately for us, I found that almost all of these papers can be classified across 1 of 3 flavors that broadly specify what kinds of behaviors you would expect from this kind of model and what kind of data it might be most applicable to. Now, I originally proposed these flavors about 1.5 years ago when we were still writing the first version of our book. And to this day, I haven't really heard anyone complain about these flavors, so I assume they're okay. Let's see. So these are the 3 different types of graph neural networks that you should be aware of if you want to encounter graph neural networks in the wild or to implement them. Here we have this convenient 3 like side-by-side view of our 3 main players and the generic form of their equations. So all of these equations, update the representation of one node based on all of its neighbors. As we said, that's the essence of our local function. And they all compute, as you might expect, a representation of some hi for node I as some kind of combination over things in your neighborhood, as you might expect. So it's permutation invariant. Okay. And there's 3 flavors: convolutional, attentional, message passing. We'll dive into each one of them in a second. But the general idea is that as you go left to right in this diagram, they will get more expressive. So they will allow you to model more complicated things. And that always comes at the expense, right? There's no free lunch. If you get more expressive, that means you have more parameters. That means you're more likely to overfit. Okay, so there is an interesting balance to be struck, and we'll actually also discuss how, in some sense, the attentional GNNs seem to be striking a nice sweet spot in the middle, and how that leads us to some very popular models nowadays. Okay, so we will now dive into some specific instantiations of these 3 flavors, and we'll discuss a little bit how to implement some of them in practice. And, it's designed with orientation in mind. Like, I'll give you a few samples of papers that are respective for each category. It's by no means a complete account. Like, even yesterday, probably some models came out that would make this picture more complete and more interesting. but it's just meant to give you an initial seed context for you to navigate and categorize everything else you encounter, okay? So that's just one important point to have in mind. And another thing, a note on notation, you will see psis and phis a lot in this part. And now, since we're talking about concrete implementations, I want to give you a concrete idea on what this psi and phi actually is, right? And they're just, neural networks that operate over flat inputs, right? And what's the simplest example of a neural network we know over a flat input? It's a fully connected MLP, right? So when I say psi of x, what I usually mean is something like weight matrix times x plus bias vector applies some nonlinearity, right? The standard thing you would do in a single layer of a neural network. If there's multiple inputs, same thing. I concatenate them and I process them together in the same way, right? So whenever you see this kind of thing, that's actually how it's implemented under the hood. And these W's and B's, those are the learnable parameters of the model. And when you do backpropagation on a graph neural network, these are the things you're optimizing. So it's actually, I actually had a really fun conversation once with someone who was just getting into graph neural networks. And he told me, when you really think about it, a graph neural network is just a bunch of MLPs that are joined together in an interesting way. And that's actually all it is, right? All the learning happens inside these guys. Everything else is just data flow that's given to you by the graph structure and the equivariance and locality constraints. Okay. And also, just to be clear, this is a single layer neural network. As you know, it's theoretically not the most expressive, but you can always stack more layers if you want to. So some people, for some tasks, like to make it a 2-layer neural network, which, as you know, from universal approximation, is the ultimately most expressive neural network, right? And typically you can train these parameters via backpropagation and stochastic gradient descent as you would train any other neural network. Okay, so let's dive into our first layer, the convolutional graph neural network. So for convolutional GNNs, we have all of these different neighbors that we have to aggregate together. So we transform every neighbor with one of these psis. And now we have to find a way to combine all the neighbors together. And in convolutional GNNs, what you do is you pre-compute an interaction coefficient Cij, okay? So before any learning happens, you analyze the graph structure somehow, and you decide this is how much neighbor J should be valuable for neighbor I, okay? And this is pre-computed, usually in a way that depends directly on the adjacency matrix. And what this means usually is that all these convolutional GNNs reduce to some kind of glorified averaging, more or less spectrally motivated, but it usually boils down to some kind of averaging. And there's various instances of how you can process the adjacency matrix to get these coefficients. The early popular example, the Chebyshev network, does some kind of a spectral expansion of the adjacency matrix using Chebyshev polynomials, so on and so forth. I mean, if you want to read more about it, you can read the paper from Deferard and others. My intention here is not to go into details of how you can compute these guys, because very often a simple average works really well. So the most popular, most cited graph neural network model there is nowadays, the graph convolution network of Kipf and Welling, basically just takes a symmetric average of the two nodes. So the Cij is 1 divided by the square root of degree of node I, degree of node J, right? It's kind of a two-way version of an average. An average would be just 1 divided by the degree of the receiver. But here you also factor in the degree of the sender into the equation, okay? And this simple expression brought about some very, empirically powerful layer that works really well on most real-world data sets, which arguably got it the amount of attention it received. Although technically, you could also claim that just because the layer is called a graph convolution network layer, that might have also helped the amount of attention it received. But what are these layers useful for, right? Because I'm just doing averaging, what kind of problems would you expect that to be very useful for? Turns out there's a very good name for the class of graphs for which this is useful. That's what we know as homophilous graphs. What does this mean? It means that edges encode label similarity. So if I am friends with someone, it is very likely that if that person likes something, I'm going to like that too, right? You tend to flock together with people who are like-minded, right? So this homophilia assumption is a very standard assumption in graph representation learning, which says if you're neighbors with someone, you're likely going to have the same label as them. And you would be surprised quite how often in real world natural data sets this assumption holds. And this is great because this model is comparably much simpler. You pre-compute all the graph interactions up front, and then you can convince yourself this reduces to just a simple matrix multiplication with the adjacency structure, right? Well, for some definition of plus, right? But basically, this is a matrix multiplication, right? And that's very easy to implement and scale up to really large graphs. So many of the industrial graph neural network applications like Uber Eats, Airbnb, and so on tend to use a model like this because often, you know, your friends will like similar foods that you do usually, or similar-ish. Your friends will travel to similar places that you do. That's usually a super strong assumption and very common, all right? But one thing that's very important is that when you have this kind of, you know, labels are shared across neighbors assumption, then you might ask yourself, yes, there's a question? I just mean labels are same. Labels are usually the same. That's it, right? And you know, when that's the thing, then do you actually even need all these psi's and phi's? Isn't it just enough to, you know, take the average of all of my neighbors and use that as my vector? Turns out it's super powerful. Like when you are at this regime, you technically don't even need deep learning. You can just multiply with the adjacency matrix many times, and then do a logistic regression. And that's exactly what the SGC model did. This created a bit of a bang in the graph machine learning community because it showed that, you know, you don't need deep learning to process homophilous graphs, and most real world data sets seem to be homophilous. So all you need to do is prepackage your adjacency matrix, multiply with it a few times, do a simple linear classifier. This works really well, remarkably well. But what should be the implication of this for us? When you're faced with a new graph data set, always test whether it is homophilous. Try a model like this. If it works really well, maybe you don't need to build any of that fancy machinery, right? Okay, but now obviously this homophilous assumption, while being true often in the real world, is sometimes just plainly false. As I mentioned at the start of this tutorial, I am very active on the social network Twitter, and I often like to retweet people. Sometimes I will retweet someone because I completely agree with them, and that's great. Sometimes I will retweet someone because I completely disagree with them, and I will enter into a rant about why what they're saying is wrong, okay? But what that means is, if you want to build a graph where nodes are linked together by retweets, you should not classify me the same way as that person I retweeted. Actually, I have a diametrically opposite label to them, okay? So in these kinds of cases, you should not rely on pre-computing stuff from the graph structure to compute your interaction coefficients. You need to dynamically compute them on the fly. So to decide how much to value each neighbor dynamically. And that's the main thing we do here, right? Compared to the convolutional GNNs, where we had a pre-computed coefficient, now you have a coefficient which is computed with a neural network. So this function A here takes the features of the sender, features of the receiver, and based on them computes one scalar value, which tells you how much you value that particular neighbor. So now the sender and the receiver collaborate to compute this scalar coefficient, okay? And to those of you who have worked with any kind of attentional mechanisms, this should sound very familiar. In fact, what I described here is an attention mechanism, right? And that's why this whole class of GNNs is called attentional GNNs. There's been a lot of interesting work in this area. Perhaps great places to get started are the mixture model CNN or the Monet, which kind of first did this in a computer vision setting. Then our own graph attention network, which generalized this to content-based attention, and the most recent incarnation of it, GATV2, which does a simple fix to this model, making it a bit more expressive, okay? And why is this such a cool class of models? It lives in the middle, right? So you have a nice mixture of capacity, scale, and interpretability. Your edges no longer need to encode homophily. Now I can compute a coefficient which says this neighbor is useless. That's great. And I can do so on the fly by looking at the features of myself and my neighbor, all right? But even though you have this new gain power, you still compute only one scalar per edge, meaning once you compute these coefficients, you can still do a matrix multiplication. So from a scalability perspective, they live nicely in the middle, right? And there's an extra nice property, interpretability, which can be a bit dubious depending on which field you're in. But these coefficients, you can interpret them as the neural network's belief of how much each neighbor is valuable, right? And you can then visualize that and maybe use that to do some basic science with these models, right? Try to infer some interesting, important linkage structure inside your graph, okay? And once again, I am never too rash with claims of interpretability. This is still just, you know, a gradient descent based training. It can latch on to anything really. But we have been able to find some reasonably interpretable things out of a graph attention network's weights inside a medical domain. So we had a graph of patients, and it actually learned to connect together patients that had the strongest interaction between one another. And lastly, sometimes not even this is enough, because convolutional and attentional models, in their heart, they just compute a weighted average of neighbors, right? There's a weighted average, right? But the receiver node plays no part in what data is sent to it, right? So sometimes that's not enough, right? Sometimes edges are not a recipe to do a weighted combination of neighbors. They're actually a recipe for passing data, like just a template for computation. And to properly support that, now you need to include the receiver node inside this collaboration. So now your psi function works on both the sender and the receiver to compute a message vector to be sent across that edge. And that's why this class of models is called message passing graph neural networks, right? And there's a lot of interesting instantiations of this model in various domains. Interaction networks, the original MPNN model, and DeepMind's graph nets are three particular interesting instances of this template. But the general idea is now, because the sender and the receiver collaborate to compute a message vector, this is now the most generic model you can do for edge level reasoning. And as a result, your edges are no longer some way to average neighbors. They're actually a recipe for passing data on the graph. And as a result, because there's a lot more parameters inside this psi than before, you might have some issues with scaling them up or with learning them properly and not overfitting. But as a result, they are the most potent model when edges truly just mean a recipe to pass the data or to do a physics process, right? So they're quite ideal when you want to do computational chemistry, any kind of reasoning or simulation tasks where truly you have these kinds of interactions between all pairs of nodes. Yes?
So this passing this way, or not really way, MIT, how does it work on the implementation of
So what's the question you're asking? Because I'm not completely sure.
Yeah. So
yeah.
It seems that the reason there is a CIJ.
Yeah. So this is a vector. That's the main difference. Cij is a scalar, and this output of the attention mechanism is also a scalar. So here the sender and the receiver collaborate to compute only a scalar, and then that scalar is used to weigh different senders. Whereas here the sender and receiver collaborate to compute the entire vector. And that's a lot more expressivity, basically. You can easily see it's a nice exercise to do, to show how these two models are just a special case of this model where you factorize the message into two parts. Yeah. Yeah, there's a question there. Yeah, you can do it. It can often be quite useful. We've done it in the context of the Google Maps project, actually. But I hope you can realize how that kind of factorization is itself a special case of this. Yeah. Question?
As far as I can tell, there's no inherent difference in scalability between the attentional networks and the message passing. Right? So
There is one inherent difference, is that you have to maintain tensors on edges. Whereas for the attention mechanism, especially if it's a simpler attention mechanism, or in some cases, if it's a dot product like attention, you don't explicitly need to store stuff on the edges beyond just a scalar. So there is a scalability benefit there.
Scatter the transform feature in the center node to each of its neighbors where it's in.
Yes, that is true. But if you're doing something like dot product attention, that's a process of just doing a matrix multiplication over matrices you already have, right? So you're not creating new data. Whereas here, you need to create a tensor of shaped edges times hidden dimension, which you don't have to materialize for some of these attentional mechanisms. Yeah, no worries. Any other questions? Yes?
If it is multiply connected graph, for example, if you want to consider effect of say V over this one, but is there a way to do it?
I mean, you do it by stacking the layer normally. And we can talk about, yes, you can do multi-hop reasoning as well, but it's still expressible using this equation. You just have to redefine what you mean by NI, right? So this, this equation here isn't too concerned with the structure of the graph. The only factor it has from the structure is this set over here. And you can define that to be whatever you need for the problem at hand. Yeah. Okay. So I want to just show you on a very concrete example how this most general class of models works, like how the data flows when you implement a model like this. And especially when you do it on message passing, which, as I said, is a superset of all the other approaches, your graphs can convey rich information on all levels. So now I'm going to break my previous assumption that there's no edge features and there's no graph features, and I'm going to introduce them just to show you the full extent of how the data flow can be, right? So we previously ignored data that doesn't live on the nodes. Now I'm going to add it back. So we assume the following set of features. First, the node features, as before. In the context of chemistry, they could be atom types, charges, how many hydrogens are attached to this atom, and so on. I'm also going to have features on the edges. So something like in the chemistry setting, what's the type of the chemical bond? Is it a single, double, triple bond? Is it in a ring? These kinds of things, right? And I might also have some features attached on the level of the whole graph. So for example, this could be the molecular weight or any molecular fingerprints you might pre-compute and stuff like that, okay? So in the most general case, I might have features on both the nodes, edges, and the graph, all right? And you can then analogously also compute latents on all those three levels. So latents in the nodes, latents in the edges, latents on the graph. And it is possible to talk about this further and talk about triplets of nodes and hypergraphs and so on. But I mean, this will be a fun point of discussion later, but I will claim that you can extend this idea to hypergraphs without really changing the template. Okay. So we'll talk about now a blueprint for a spatial GNN, which generalizes all the flavors you've seen so far. That's DeepMind's graph network model. I use it because it's the first model proposed that truly operates over all three of these types of inputs simultaneously, even though you can obtain these interaction networks and message passing networks just by restricting the equations slightly, okay? And our general strategy for one layer data flow is you first compute your edge updated features by using the graph and relevant nodes. Then you update the node features by aggregating over all the edges that send to that node. And finally, when you updated both the edges and the nodes, you update the graph features by doing a permutation variant sum of all the nodes and all the edges, right? And use that to update the graph. And of course, use a lot of skip connections, because when you have a model that's this expressive, putting skip connections is always a good idea to make the model learn a bit better. So first part of the strategy, updating our edge features. So we compute these latent vectors in edge UV by our first learnable NLP that looks at node U, node V, so the two nodes involved in this edge, any edge features we have, and the graph features, right? That's the first step of our data flow. Once we've computed all the edge features, we can interpret them as messages and send them into the nodes. So this is the second step. We update the node features, HU, by applying a function to that node's features. That's the skip connection I told you about. It's great for preserving learnability. And then we sum up or aggregate all of the edges features that send to that particular node and also use the graph. Okay. And now you might imagine when we have both edges and nodes, we can finally update the graph by permutation and variance strikes again, sum up all the nodes, sum up all the edges, graph features. Yeah. So this should hopefully make sense using the building blocks and principles we've discussed before. Are there any questions? Okay. So let's give you a visual interpretation of what you just saw. Imagine I have, a graph where I maintain features. So I have these X's in the nodes, I have X's and edges connecting them. I have an X for the whole graph. So I first, as I said, update my edge features for this particular edge using all of these pieces of information, right? The two nodes, the edge itself, and the graph. Once I have all the edges, I can use that data to update the node features by using the node itself, the graph, and the aggregate of all the edges that send to that particular node, right? And that goes into my second function that updates the node features. This process, by the way, I've been asked this question recently. This process is repeated for this node also, but I didn't draw it because this picture is already quite full as it is, okay? And now finally, when we have the nodes and the edges features updated, we can update the graph by summing up all the edges, summing up all the nodes, and using the previous graph. And this is it. This is the whole data flow of one step of a graph network layer. And it's a really fun exercise, first of all, to see that all of the ideas I told you before, permutation, invariance, and equivariance, you can color code all these data flow edges by which ones are equivariant and which ones are invariant. So this idea permeates across this whole template. And further, it's now a really fun exercise to, once you read some interesting GNN papers, like some of the ones I recommended, to specify specific choices of these three functions, psi, phi, and rho, to reinvent all those different models as special cases, right? And this is what I meant when I said that I got that comment from a colleague saying, isn't GNN just basically a bunch of MLPs carried together? Yes, it is. MLP1, MLP2, MLP3. You've learned these three guys, that's your GraphNet. That's it. Okay. And I want to give you one final food for thought before we move on to some more advanced topics. After I've introduced deep sets to you, I was able to show you that there is a rigorous proof. I wasn't able to go through the proof. I didn't have enough time, but you can trust me. There is a paper that has a proof that any set function that works, any set function that's permutation invariant, can necessarily be expressible as deep sets. So in that sense, deep sets are universal for learning on sets. Is this thing equally general? This thing of define a one-hop neighborhood and do message passing over that? Is that equally general? Can I use it to represent any permutation equivariant function over graphs? It's a very fun question to think about, and I hope I've given you some food for thought, and I hope I'll give you some possible answers to this question as we go on through this tutorial. Okay, so I think we should have enough time for this session to also cover latent graph inference, and then some of the other topics I wanted to cover, we'll cover them in the next hour. So we'll talk about latent graph inference. What is it in a nutshell? It is graph neural networks without the graphs. It sounds a bit blasphemous, but we will discuss and see how not only is this a very common situation, but it's also a very important situation if you want your graph neural network to actually do science. And also studying graph neural networks from this angle will allow us to connect them to some of the most popular models there are out there right now. Okay? So what do I mean by latent graph inference? Basically, I want to challenge an assumption I kept making from the start of this tutorial, which maybe some of you realized, maybe some of you didn't, but I always assumed there is a graph. Like I always assumed I have a collection of edges I can carry around and build an adjacency matrix out of and use them as a template for message passing. So I've assumed that some ground truth God-given graph is given to us, okay? But this is actually not an innocent claim at all. Here's one very simple example, common in physics, right? You have a bunch of particles. They interact together with forces like gravity, electricity, and so on, right? All of these forces are usually not directly visible to us, right? All we can see is how these particles move in three-dimensional space. So we have to somehow look at these trajectories and figure out what's the underlying graph. That's how we do science, right? Figure out what are the connections between these particles. Yeah. So basically, in most naturalistic setting, a graph is not given to us. If we have any graph, it's the result of applying a human heuristic. Okay, and that's often not perfect, if at all. And basically, the idea of how to do graph representation learning without a graph is the idea of latent graph inference. And in my opinion, it's one of the key emerging areas of the field. And it's an area of very high interest to science, because if you do it properly, you'll be able to look at a collection of particles like this and tell me exactly what are all the forces between them, right? That could be really cool. Also to infer a causal model and causal structure of the world and these kinds of things. And also, beyond the fact that it's useful for doing science, it turns out that if you study some standard approaches to doing this problem, you'll end up discovering connections between many state-of-the-art models and GNNs. Here's a spoiler alert. Almost everything we discover will be a special case of a GNN, as you might expect by this point. So first of all, I want to stress just how important this point is, because, okay, you might also assume that your input graph is absolutely correct. Sometimes this happens. It's super rare in the real world, but sometimes it happens. Even then, that might not necessarily be the optimal graph for the problem that you want to solve. I'll give you a simple example. Imagine I have nodes in the graph, and I want my network to predict, are two nodes connected? Like, do they, is there a path from one to the other? Okay. Now you can imagine how, if you apply a graph neural network to the graph, if I'm very adversarial about this graph, you might need a linear time complexity to answer this question, right? Because I could give you a long path and give you two nodes at the ends of this path, and your GNN must propagate information across this path until it connects these two nodes, right? However, if I choose to represent edges of my graph in a slightly different way, specifically for those of you who are computer scientists by training, you might have heard of a disjoint set union data structure, which basically allows you to answer these questions of who's connected to what in time complexity, which is the inverse Ackermann function. And for any astronomically sensible number of nodes, that's less than 5. So even if the graph is perfectly correct, if you message pass over the original graph, you'll find the answer in linear time. If you message pass over a slightly different graph, you'll get the answer in almost constant time. So choosing the right edges can be a very interesting problem, even if the graph is perfect. Okay. So in general, even if you have a good graph, rewiring it for the task at hand might be a good thing to do. That's just a general thing I want to impart on you. But what I want to do in this particular part of the talk is take this to the extreme. What if there is no graph whatsoever, but being scientists, we assume that an underlying graph might exist, right? So what this means mathematically is I've given you a node feature matrix X, but there is no adjacency structure. There might also be edge and graph features as before, but I'll ignore them just to keep things simple, okay? And, you know, when you think about this, what to do with node features and no graph, I mean, you've kind of seen a solution for this already, right? Remember deep sets? That was basically a model for a bunch of nodes with no graph. It's a bit of a pessimistic approach, though, because as I said, with the set assumption, you're assuming that there are no edges to begin with, right? And that's kind of equivalent, if you look at the equations of deep sets, to assuming that your adjacency matrix is the identity, or equivalently that the neighborhood of a node is just the node itself. Yeah. And what this means is that any aggregation you do inside the equations of a GNN is equivalent to just pulling out the receiver node's features. And therefore, any graph neural network, convolutional, attentional, or message passing over a graph like this reduces to this equation, which, as you know, is the equivariant part of deep sets. So we actually made our first fun connection. There is an approach to do latent graph inference with no graph by assuming there is no graph to begin with, so no connections whatsoever. And it turns out it's deep sets. So deep sets is actually a graph neural network where you make the specific assumption that there's no graph. Yeah, or well, that this graph is the identity. Can anyone maybe suggest another approach we could do? Yes, fully connected. So I can assume no edges, or I can assume all edges, right? It's, if the previous approach was pessimistic, this one you might call it lazy, right? Like you don't have any idea, you don't want to bother trying to find out what those edges are. So let's just assume everything is connected and let the network figure out by itself what are the important edges, right? That's a very popular approach. So mathematically, it means you take your adjacency to be the dot product of one's vector with itself, the outer product of one's vector with itself, sorry. So this is basically a matrix of all ones. And equivalently, the neighborhood of every node is all the nodes, right? Now, one very interesting point is, if I were to apply a convolutional GNN, if you remember the 3 flavors, the convolutional GNN applied over such a graph will reduce the deep sets one more time. So this is very interesting. Like basically, it's a very fun exercise to prove to yourselves that if you go away and do this, you'll end up with basically the same model as deep sets, because that second aggregation will be the same no matter what node you are. Yeah. So what this means is that maybe we should try something a bit more expressive. So as we know in the hierarchy, convolutional is followed by attentional. So let's try attentional. Here I've just copied back the equation of an attentional GNN where I replace the neighborhood with just the set of all nodes. Everything else is the same. Can someone tell me what the hell am I looking at? This model should feel a bit familiar. Yes, exactly. So this should feel a little bit like a transformer for those of you who have done any natural language processing or just heard about transformers otherwise. But I do not want to kind of start at this point and then immediately say, hang on, I've just showed to you that, you know, transformers are a special case of GNN, blah, 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 right? I want to actually take a step back and motivate this whole discussion from the point of view of someone who uses transformers for natural language processing, so that hopefully we can all agree that this connection exists. And what I'm going to do is I'm going to take a natural language perspective, and I'm going to rederive transformers without ever mentioning transformers. Okay? So, as mentioned, some of you probably saw this equation and recognized the famous language processing model. I'm not going to tell you what it is, right? I'm not going to mention the word, I'm not going to mention that word, right? In fact, this is one indication of a long-standing alignment between NLP and the graph representation learning, because many old school node embedding methods, which is what we used to use before graph neural networks became popular, they were very correspondent to word embedding techniques. In fact, if you do this kind of correspondence, nodes to words, random walks to sentences, you end up with node to vec, which is basically the same thing as word to vec, same optimization objective, just the data is different. Yeah. And this carries on to this day. Very recent self-supervised methods for graph representation learning are quite commonly borrowing concepts from methods like BERT. I'm not going to say which model is based on BERT. I'm just like, it's BERT. But what's very important is that we can flip this on its head and take this correspondence in the other direction as well, right? So, in natural language processing, we are typically interested in processing data that is words in a sentence, right? And it's either for the purpose of classifying the sentiment of that sentence, so is it positive or negative, or translating it into a different language or something like that. And, if you look at it, the words in a sentence interact with each other, right? There is an interesting graph structure in there. Subject, object, adjective acting on noun, and these kinds of things, right? And specifically, this interaction is not trivial. So there's very interesting connections in there. And it's not sequential, right? It's not just one word interacts with the next word. These interactions can span even multiple paragraphs. Like a modifier you place at the beginning could refer to a word 5 sentences later, right? And this is actually one reason why you shouldn't use an LSTM for this, because it subtly assumes that there is a linear graph in the problem you have, right? So we might want to use some interesting non-sequential graph between our words, but we don't know what this graph is. What is it, right? In fact, not even human annotators tend to agree what this graph is. And actually, depending on the problem that you're solving, you might find a completely different graph to be most useful, right? The graph best for classifying sentiments of sentences and graph best for translating from English to German might be completely different. Like the optimal graph might be completely different. So what do we do when we don't know what the graph is, but we know that there is one and it's complicated? As we said, use a complete graph and then let the graph neural network infer relations by itself. Yeah. And by far, the most popular approach then is to use an attentional GNN over such a graph. And this gives us one of the most recognizable deep learning models of today, right? And that's a transformer. Okay. So if you take a graph neural network over a fully connected graph of words and use the attentional flavor, you have exactly rederived the equation of a transformer. And at no point did I mention transformers in this exposition. I just said there are words, there's a graph between them, you should use a GNN, and you don't know what this graph is, so you should use a fully connected GNN, right? So I basically rederived transformers without using any transformer-specific lingo, and that's a pretty important kind of note that transformers are a special case of attentional GNNs. And you might be wondering, okay, but what about the sequential information in the words? Isn't the graph neural network permutation equivariant? Like, these words should have a sequential structure to them. Well, a transformer fixes that by putting these positional embeddings in the inputs. But those are just extra features that tell you a hint as to where this node is in the graph, right? The model itself doesn't have to use those features whatsoever. There's no mathematical constraint that those features need to be used, right? So if you drop them, you'd end up with a fully connected graph structure, but nothing stops you from putting positional embeddings in graphs either. Like that's a very standard thing to do, yeah? And what this means then is now this attention mechanism with its coefficients is a way to infer a soft adjacency matrix and letting the GNN choose its own edges, okay? Now, this connection is very, very beautiful. I could dedicate basically half of a lecture just talking about how these equations line up from the data flow point of view. I don't have enough time to do that. However, Chaitanya Joshi, who is actually in the audience today, has written a very beautiful blog post, which is titled this way, Transformers or Graph Neural Networks. So it's very easy to find. And I highly encourage you to read through it and convince yourselves that these two things are actually the same. And I want, before kind of rounding off this part, I want to also make one philosophical mention on why attention specifically and why transformers are so popular nowadays. Why is it exactly this GNN that is winning? Well, first of all, if you look at what it's working on, words, they're kind of meaningless without any context, right? A single word doesn't have any meaning, but a word combined with other words gains meaning. And therefore, the input features to the nodes are just one-hots, right? An index into a vocabulary of words. And that's unlikely to give you complex messages. So there's no need to do message passing, right? Actually, representing words as weighted combinations of other words is a pretty fair way of looking at it. So attention aligns really well with this kind of computation. And most practically, because it's a dense matrix multiplication oriented system, it can be used for massive scale language models with billions of parameters like GPT-3. And therefore, because also it has a more favorable storage complexity than message passing GNNs, where you need to store an extra vector for every single pair of nodes. This means you align transformers really well with GPUs, right? So the hardware we have right now is really good for executing these kinds of models. So one different way of saying this is that transformers, you can think of them as graph neural networks that are winning the current hardware lottery. They are the model that is best suited for the model of computation that we have right now, and it conveniently supports a graph structured reasoning over the graph of words. And if you want to, the hardware lottery is a very fascinating thing. And if you want to learn more about it, Sarah Hooker wrote this really nice piece for Communications of the ACM, where she talks about this phenomenon in detail. And I'll just note that for some problems, attention is not enough to model the interactions. And in those cases, you might want to use the message passing flavor, and it seems to work quite well also. So this is the equation of a message passing GNN with all the nodes used as neighborhoods. And in these cases where you need to do things like physics interactions or relational reasoning, you need to compute forces and these kinds of things along the edges of your graph. So message passing may be more expressive than transformers. And these are the kinds of domains where transformers don't seem to come out on top in terms of their performance. And interaction networks did this first for physics tasks. Relation networks did it for visual reasoning, and they achieved very early on superhuman in performance on the clever data set. And they all rely on the same idea: build a graph of all of your objects together, fully connect it, and do message passing over them. And the last point I want to make before we go on a half-hour break for coffee before the next parts is that the truth, the real truth actually lies probably in between, right? Like I gave you two solutions for handling this problem. The empty graph, the deep set approach, which, as we know, ignores a wealth of connection information. The full graph, which connects everything to everything, which seems to work great when you're okay with a lazy approach and you can handle it with a number of objects. But, there's a quadratic space constraint. There's a lot of large neighborhood constraints. This is not easy to scale up, right? Even though it's theoretically going to give you all you need. And many recent developments on transformers try to do some tricks from GNN literature to scale them up, basically to sparsify that attention mechanism, right? So transformers are also becoming more like GNNs when you scale them up to much larger contexts. But what do you actually want, right? You want to somehow figure out the adjacency matrix A, right? And actually infer a masked adjacency matrix A and use it as edges for a GNN. And this is what we commonly call latent graph inference. The reason why it's so challenging is because choosing edges, like discretely deciding what edges to use, is a discrete decision. You cannot propagate gradients through that. So you cannot end-to-end pick edges and use them in a way that's learnable, right? So there's a lot of recent interesting approaches that try to do this, recognizing that it could be quite useful for doing science with graph neural networks, because these graphs can then be used as an explanation for what's going on inside your system, right? And there's 5 recent approaches that build a graph, discretely sample it, and then use it for a GNN. There are probabilistic approaches like the NRI model. There are models that actually use no learning at all, which is great. Like they non-parametrically decide the edges on the fly by k nearest neighbors in the embedding space. And this allows you to actually backpropagate through everything with no problems. Obviously, this might have issues with how stable those graphs are, but the DGCNN model, which does this, is quite powerful in the point cloud domain, actually. Then there's its spiritual successor, the DGM, which uses reinforcement learning to select edges. Discrete decisions, reinforcement learning might be a good idea for that. You can also, as in our PGN paper, use fully supervised learning if you have some belief on what the edges might look like, but you want to then use that knowledge to expand to a different, manually learned set of edges. And finally, the SLAPS paper, which recently came out at NeurIPS, is quite groundbreaking because it is the first paper that tries to do a self-supervised approach to learn the edges. And in reality, that's really a good idea, because if you have to drive the decision of n squared different things based on a downstream label, that's quite sparse, right? But if you somehow make it self-supervised, make every node contributes to the final output, then suddenly you have a lot more signal to learn these edges from. So they add this interesting denoising objective, right? They make you pick the edges that would denoise the graph's features as good as possible. And that's actually where we're going to stop for the second part of the tutorial. We will see each other again in half an hour, where we'll talk about how powerful these models are and where to go from there. Thank you.